Alright, we're going to skip section 2 too. And you'll be very grateful that we skipped 2 too. Okay? I have taught it before in the past, but man, it was like pulling teeth. So I thought, oh, I'm just going to skip it. And you should be very happy about that. Who knows, you might look at this and say, well, this is no better. But I like this stuff. This stuff, I think it's a little on the easy side. It's just a little bit weird. You just have to get used to a couple rules. If you can follow a couple rules, you should be able to do this stuff. And you probably did this in Algebra 2. And it's called complex numbers. Does that ring a bell? Yeah. What feeling comes to your mind when you think of that? Difficult? Why? Because the word complex. Look, the word complex doesn't mean difficult. Now, I'm sure it does in some. There are, there's a lot of different definitions for words and things like that. But the word complex for us isn't going to really mean difficult. Okay, what it means is it's a combination. It's a combination of two types of numbers. Okay, one would be a real number. We'll use a as a real number, and then we'll just add it to this, bi. Do you remember that I stuff from Algebra 2? All right, they're not fake numbers. Imaginary numbers. They're not fake. They do exist, okay? It's a little unfortunate that they use the word imaginary because the numbers do exist. Now, they don't exist on the real number line like we're used to. You know how we do a number line? And, you got 0, 1, 2, 3, negative 1, 2, 3, and all that kind of stuff. These numbers right here, these i's, don't exist on a real number line. And the complex number, remember, it's a combination. You remember English class when you used to do grammar and stuff. Remember you had like simple sentences, compound sentences, complex sentences. Wasn't a complex sentence like a it was like a combination of what? Like a simple and a compound or something like that? I don't know. I can't remember exactly myself. I should ask an English teacher and they could tell me. But I think it's a combination between two different types of sentences, right? It's one sentence, but it's like a combination of a simple and a compound, or two compounds, or something like that. I'm not exactly sure. But that's basically what we're talking about when we talk about complex numbers. It's a combination of a real number. So this A represents a real number. Well, you say, well, what's a real number? A real number is any number that you've dealt with in the past. Any number that you can put on a number line is a real number. Okay, this right there with the I is not just a variable. Okay, the I is actually a number that actually does exist, but it doesn't exist on the real number lines. And this is the imaginary part. So it's got two parts. It's got a real part and an imaginary part. And notice, the real part goes first and the imaginary part goes second. And that is important. Just like the number, I don't know, 32. Does it make a difference which order that 3 is and that 2 is? Sure, because if I put it in a different order, that would make a different number, wouldn't it? It's not an exact analogy for this thing right here, but it's close enough for you to kind of understand a little bit. So it is important which one goes first. I mean, some teachers, they're probably not real picky on it. Some teachers are very picky on it. I'm going to be a little bit picky. All right, it's not that difficult to be picky on this. It's not that hard. You put the real number first and the imaginary number second. Here's an example: 3 plus 2i. That looks like two separate numbers right there, but it's not. It's one complex number. This thing right here is one number, and it's a complex number. I actually took a class in college, math class, and it was called complex analysis. And what it was, it's like doing every math that we had ever done, but doing them with complex numbers, okay, and with I. We did trig with it, we did calculus with it, we did all kinds of stuff, algebra, and all that kind of thing, with complex numbers, a whole entire course on that thing. I probably wouldn't have minded the class so much if it wasn't for the teacher. I couldn't stand the teacher. He was just an arrogant, I'll be nice since I'm being recorded. No, I would be nice anyway. I'd be nice anyway. But he was just arrogant. He was like a blowhard. He was just a Mr. Know-it-all. And I just couldn't stand it. But I won't even say his name. But I don't think he's there anymore anyway. But he taught complex analysis, and I think I would have enjoyed it more if I would have had this other professor that I really liked. That was Dr. Wooldridge. He was really cool. I had him for calculus. Really super nice guy. Great personality. he was like no nonsense. I kind of try to teach like he does sometimes. He doesn't go off on tangents like I do from time to time, but he told some stories every once in a while. But he was just kind of nice. He just taught. He didn't stand on his head, do tricks and games, and all that kind of stuff. He just taught straightforward. But that's what I liked. He wasn't cocky. He didn't have, but he was probably the smartest guy that was there. But you would never known it by his attitude, and he was really cool. Anyway, that's complex analysis. Okay, let's talk about that I for a second. I is actually a number. It's defined. Let's do this. Let's change colors. Get rid of that. Let's go, I don't know, let's go to mint julep. How's that sound? Let's talk about the letter I. The letter I is defined. This is a definition. The letter I, in this kind of notation, is defined as the square root of -1. There it is. That is really, that's kind of like your foundation for this stuff. I is equal to the square root of -1. That's very, very important. For instance, if I said if I said the square root of 16, what does that really mean? What am I asking myself if I do the square root of anything? I'm asking what number what? Times itself. Okay, so what number, right, times itself is equal to what? 16. You see that? So what number times itself? So what times itself, not just what times what. Okay, what times itself is equal to 16? It's 4. So x is 4. Would you agree? So the square root of 16 is 4. It's pretty easy to see, isn't it? What if I did this, though? Well, we could even do a number that doesn't come out nice and even. Watch this. What about the square root of 5? The square root of 5 is what times itself is equal to 5. Would you agree? All right, so what number times itself is equal to 5? Well, is there whole numbers? Is there a whole number that if I multiply by itself it's going to be 5? No, there's not. But think about it. 2 times 2 is 4, right? 3 times 3 is 9, so it's got to be somewhere between what? 2 and 3. You see that? So I can just look at this and I can say, oh, this has got to be 2 point something. Daniel, what'd you get?
About 2 point.
Right, about 2.24. Okay, that kind of makes sense, doesn't it? Do you see that? Because the square root of 4 is 2, the square root and the square root of 9, right, is 3, so it's got to be 5 lies somewhere in between the two, and there it is, it's 2.24, and it's a little closer to 2, isn't it? Right, because 5 is a lot closer to 4 than it is to 9, so this decimal's got to be a little bit closer to 2 than it would be to 3. Get it? Okay. What if we did this, though? Since I'm changing, we'll go this raspberry looks too much like that. Let's just go global squash. Somebody in my other class loves global squash. Every time I ask them, they'll say, I want global squash. I don't know why. Don't know why. All right, let's take a look at this. What if I had this? What if I had the square root of -9? That means what number times itself is equal to -9? 3 times 3? 3 times 3 is not -9. What about -3? Because -3 times -3 is what? It's +9. Just think of the rules of multiplication. If I multiply two things together, whether they're and they're the same sign, if I multiply, let's say it this way, if I multiply two things that are the same together, that means they're either both negative or they're both positive. What's my answer always going to be as far as the sign's concerned? It's always going to be positive, right? Negative times negative is positive. Positive times positive is positive. You see that? All right, so look at this. Can I take a number and multiply it by itself and get a negative number? Can't do it. It's impossible because of the rules of multiplication. So this looks like I can't do it. You got a calculator? Put it in the calculator, see what it tells you. It says error. That's right, because it doesn't do it. Because the calculator is only using real numbers. Okay, the calculator that you use only works with real numbers. So what we have to do is we got to come up with something else. And this is it right here. Okay, that's that definition. I is equal to the square root of -1. So what we're going to do is take this, the square root of -9, and we're going to break it down into 9 times what? -1. Isn't that the same thing as the square root of -9? Now watch what we're going to do. Let's break this down. Remember, you can take the square root of both of the things in there, right? If it's being multiplied. We've talked about that before. So I can go the square root of negative, or square root of 9 times what? The square root of negative 1. Okay. Now let's do this. What is the square root of 9? It's just plain old 3. Now by definition, what's the square root of negative 1? It's I. That's right. So what we do is we write it as I, and that is my answer. That's what this is equal to. Now you won't be able to verify that in a calculator because your calculator doesn't deal with i's. Right? But that's what it is. So see what I did? I basically just pulled that negative out. When I take the negative and I pull it out, what does it become? Well, no. If I pull the negative out, what did it become? It became an I, didn't it? Okay, because that square root, or the negative inside of a square root, if I take it out, that just becomes an I. So, for instance, what if I did this? What if I did the square root of negative 17? What would that be? So basically, what do you do with that negative? It becomes a what? An I. Do you see that? So if a negative is inside a square root, basically what you can think of it as just becoming an I. What do we have left then? Square root of 17. So this is the square root of 17i. See that? Now sometimes, it depends what book, what author, what teacher, and all that kind of stuff. It really doesn't make any difference. A lot of times, see, that I is not under the square root anymore, is it? Because the negative was, we pulled it out of the square root, and so that I is definitely not under the square root. Sometimes, though, people will accidentally make this a little bit longer, and it makes it look like it's under the square root. In order to combat that so that it doesn't look like it's under the square root, some people will write it like this. They'll write I square root of 17. It means it's the same exact thing. Okay, doesn't make any difference. But this way, you just don't get confused with, is that I under the square root or is it not under the square root? Well, it's definitely not here, is it? All right, so it doesn't really matter. I probably stick to this way right here. But a lot of students say, hey, you know, I don't want this to be confused as being under the square root, so I'm just going to stick it out in front. And that's perfectly fine. It doesn't really matter one way or the other. I'm just telling you, if I was to do it, I'd probably do it like this. But this would be perfectly fine as well. Make sense? Alright, so we know a little bit about imaginary numbers now. Let's do a couple little rules here. What about this? Let's change colors. Let's go to, let's see what raspberry looks like. We'll do Hawaiian blue next. Let's do this. There are rules for this that I'm going to do right now. Does it kind of look speckly up there? Yeah, it does here too. That's kind of crazy. Alright, that's okay. Looks kind of funkadelic. You ever hear that word? Back in the 70s. Funky, you've heard that, right? Funky came from the word, it came from funkadelic. It's not a new word, that's an old word. Parliament and the Funkadelic. You ever hear that? That was a group. I almost went to a Parliament concert. My friend across the street, he's a black guy, and he's like, well, there's a point to this. He was going to take me to a Parliament concert, right? And because I was listening to the music a little bit, I knew some of the songs. I'm like, yo, Brian, man, take me to the, you know, see Parliament. Yeah, they're going to be in Philadelphia. But he tried to talk me out of it. He says, dude, you do not want to go to a Parliament concert because, I mean, it's all black and it's all like militant too, you know what I mean? It's like, you know, I would have definitely gotten it, you know, if I would have gone there. So he was a good friend, and he talked me out of going. He's like, yeah, it would be cool, you would love it, but you don't want to go. I'm like, all right, I guess I won't. So I was watching something on TV the other day, and they had Parliament like way back in the 70s in concert. You have any idea who I'm talking about? Is what's his name? George, the main guy for him. George Clinton. George Clinton. Look him up. George Clinton. This guy's crazy. He's a really cool guy, but I mean, he had, I can't even explain to you. They were nuts. And their music is so tame compared to today's standards, but back then, I mean, they were cutting edge. They were wild and crazy and everything else. And we look back on it today after seeing all the stuff that we've had since then. You're like, what? You got to be kidding me. People like that stuff? But it was kind of cool. Anyway, how did we start talking about that? Parliament. How did I, what is it? Funk. Oh, the colors, right? The purples, funkadelic. There we go. I always like to figure out where I started from. Okay, let's do this. There are rules for this. There are rules that if I multiply the square root of two negatives together, you get something. Okay, there's a rule if I multiply the square root of a negative times the square root of a positive, then I get something. I'm not going to try to learn these rules because... Okay. Sorry, just little things like that. There are certain rules for that. But I think it's a lot easier just to break them down into what we just did right here every single time, because the rules can get confusing, and I think too many rules is too much, you know. So I just remember this basic rule, and then I can work with any of these. It doesn't make any difference. So what I'm going to do is I'm going to take that square root of negative 7 and simplify it. Oh, by the way, you know what I forgot? I forgot this one thing. Let's do this. What if I had I squared? What's I squared equal to? Well, it's I times I, isn't it? Would you agree? Well, what is I equal to? Square root of negative 1 times the square root of negative 1, isn't it? Well, let's think about it this way. It's a little bit easier to do it this way. I squared. Well, I is square root of negative 1, and if we square it, what if I take a square root and square it? What does that square do to the square root? It cancels them out, doesn't it? You see that? So what's I squared equal to? It's just negative 1. There's negative still in there. Didn't cancel out the negative, okay? The square and the square root cancel each other out. Does that make sense? All right, so what's I squared equal to? It's equal to negative 1. That right there is a real big deal. You're going to use that a lot. All right, so keep that in mind. So I squared is the same thing as negative 1. All right, which is a real number, isn't it? Isn't that kind of weird? If I take two imaginary numbers and multiply them together, I actually get a real number. All right? So that's going to help us a little bit right here. So let's do this. Let's break down the square root of negative 7. Remember what I did with this? Whenever you see a negative, what do? You throw it outside of it, and it becomes a what? An I. So this is going to be the square root of 7i, right? And this is going to be what? The square root of 7i. See that? So square root of 7i for this one, square root of 7i for this one. Now what I'm going to do is this. Let's group the things together. Square root of 7 times square root of 7. What is that? It's just plain old 7, isn't it? Square root of 49, square root of 49 is 7. Now look at this. I got an I times an I. Well, I times I is I squared. And now we just learned a second ago what I squared is equal to. What's I squared equal to? It's negative 1. Okay, so what's 7 times negative 1? It's negative 7. Alright? Let's do this. What if we did this? Had the square root of negative 7 times the square root of positive 7. Now on that one, that rule kind of actually makes sense, because look, if I'm multiplying it by itself, what am I doing to it? I'm really squaring it, aren't I? So what I'm doing is this. I'm taking the square root of negative 7 and I'm squaring it. That square cancels out with that. What are you left with? A negative 7. So that kind of makes sense, doesn't it? What about this one, though? It kind of looks like, oh, negative 7 times 7 is negative, right? But let's think about it. The square root of negative 7 is what? The square root of 7i. Well, the square root of 7 is just the square root of 7. There's no I on this one, is there? Because there's no negative inside of that square root. Now let's multiply these together. What's the square root of 7 times the square root of 7? And then what do we have left? We still have that I, so that's 7i. You see that? You could look at it another way. You could look at it like this. Well, square root of negative 7 times 7, I could just go negative 7 times 7 inside the square root. And then I could go the square root of negative 49. Do you see it? And then pull that negative out of there. That becomes an I. What's the square root of 49? It's 7. So you can get it either way, can't you? All right, so there's a couple ways of looking at these. All right, I think it's important to be able to take each one of these and break them down, because sometimes it gets a little confusing if you don't realize that. All right, what are we doing? Hawaiian blue. Okay. All right, let's check another one out. What if we had division? What if we had the square root of negative 20 over the square root of negative 2? Again, you could do this a couple ways, but here's my preference, okay? It's a preference. You don't have to do it like this, but this is my preference. What I would do is this. Whenever you see a square root and a negative inside of there, what's it going to be? It's going to be an I, right? Take that Take the negative out of the square root, becomes an I. We've done that 3 or 4 times now, haven't we? Okay, and then what's going to be left? Square root of 20. Just to be different, I put the I in the front, okay? Just to show you that it doesn't matter if it goes back here or in front. It doesn't make any difference. Okay, what's this going to be? Take the negative out of the square root. What does that turn into? It turns into an I. And then what's left over? Square root of 2. You see that? Now look, what's I over I? What's anything divided by itself? Yeah. Even if it's a square root of a negative. If it's the same thing, if it's a number over itself, they just cancel each other out. And so what do we get here? You could make it one big square root, couldn't you? And put 20 over 2. Correct? And then what's that going to be? The square root of 10. And there it is. Okay, so that thing right there is a square root of 10. Again, you could have looked at it another way. You could have taken this and said, oh, well, that's one big square root, and it's negative 20 over negative 2. Right? You could have done it that way. Might even be less steps. I don't know. Watch what happens. Negative over negative is positive. 20 over 2 is 10. There you go. You can get it either way, couldn't you? Alright? I just like to do this because there will be times when it's very important to be able to break it down from here to here. Okay, that was kind of easy. To do this problem, this probably would have been a little bit easier. But we're not only trying to just learn how to do the problems, we're trying to learn some other stuff as well. Alright? Let's see what else we have. Hang on just a sec. Okay, what we're going to do is we're going to take those imaginary or those complex numbers and we're going to add and subtract them together. This is no more difficult, I promise you, this is no more difficult than when you first started doing pre-algebra or algebra 1, when you first started adding like terms together. Alright, I promise. Let's try, what haven't we used yet?
All the way down.
That's all the way down. Well, almost. Yellow, let's use yellow today. Sunshine? Okay. It's a little bit duller than the yellow. But what we're going to do is we're going to add and subtract. Watch. What if I had a plus bi, that's a complex number, correct? Plus c plus di. Well, if you had something like this, all you do is you add the like terms. So add the real numbers. Okay, I'm not just saying add the constants. Okay, I'm adding the real numbers. Which are the real numbers? The a and the what? The c. So all I could do is just a plus c, correct? What about the i's? bi plus di, right? Plus bi plus di. Okay, no big deal. But watch, this is one way we want to write it. So a plus c plus, so that's your real part. You don't really have to put it in parentheses, but I'm just going to. And what's your imaginary part? Watch this. b plus d, factor out an I. It's got an I in common, doesn't it? So put the I out here. So that's basically what it is. All right? That's probably even more confusing than what you're going to actually do in these problems. Let me give you an example. All right? This is actually pretty easy stuff, I think. And then negative 2 plus 6i. Okay, here we go. It's as easy as this. It's just adding like terms. It's really simple Algebra 1 stuff. So what do we add? Add the reals and then add the imaginaries. So it's 3 plus negative 2. What's 3 plus negative 2? It's just a 1, isn't it? Yes? Anybody following along? Okay. Nod or something. So 3 plus negative 2 is 1. And let's add the imaginaries. What's the imaginaries? Negative 4i plus 6i. What's that? It's 2i. So we put plus. It's a positive, so we put plus, and then 2i, and then you're done. That's all there is to it. Told you it was easy. I wouldn't lie to you, would I? I didn't hear much. Let's do another one. Now, that's addition. We could do a subtraction as well. But you know the rules for subtraction. Uh, 13 minus 15.
It'd be cool if you have a thing like every time you have to go to the internet, it would change different color on the rainbow, and it would like maybe a cycle.
All right, let's do this. Look at this. This is addition. Again, what are we doing? We're just adding like terms, aren't we? But what do we do with that minus sign? This parentheses is important. To tell you the truth, these parentheses right here didn't really do anything for us as far as our math was concerned. Okay, they just grouped this complex number and they grouped this complex number. What about this? We have to distribute, right? So I'm going to go negative 9 plus 7i. What's this? Minus 3. What? Plus 15i. Good. And now I can add my like terms. Add the real numbers first. Negative 9 minus 3, that's negative 12. And add the imaginaries. That would be plus 22i. I told you this was easy, didn't I? Yeah. And that's basically it right there for addition and subtraction. Now there is multiplication. We'll do that tomorrow though, okay? I split this up into two. I thought I was going to do it in one day, but I did split it up into two. Alright, so that's the kind of stuff that's going to be on the worksheet. Alright, it's not too bad, is it? Should be pretty easy. Alright, that's it. I'll give you the worksheet and then you can do that tonight.